Okay. So hope everyone is doing all right. Are there any questions before we begin? Okay, so I will remind you very quickly what exactly we covered last time. We were talking about the cutting plane idea. So we have introduced the cutting planes. We have explained that the more cutting planes they are, like basically a cutting plane is a hyperplane that separates a point that does not belong to the set over which we are doing optimization from the set over which we are doing optimization, right? And we have realized that when we are solving relaxations, we normally getting points that are outside of our feasible set, and for those points we can construct those cutting planes and add them to the, for example, linear programming formulation, so that our linear programming relaxation will cannot converge to the same point anymore. And hopefully if we add enough cutting planes, we will eventually get a linear programming relaxation that results in a feasible point, and therefore solves our problem. And then we have formulated the Gomori fractional cutting plane algorithm that consists in the following kind of steps. First, you solve a linear programming problem, like a linear programming relaxation of an IP. This linear programming relaxation gives you a separation of the variables that you are considering into basic and non-basic, and you basically the solution of the linear programming relaxation provides you with a reformulation of the problem in the following form, right? With the new coefficients a bar in the objective, and the new coefficients a bar in the constraints. And in terms of these new coefficients, you actually can construct a new CG cut, a new CG kind of valid inequality that cuts off the current solution to the linear programming relaxation that you have obtained on step one. When you have obtained this this new cut, you can add it to the linear programming relaxation and resolve the problem. This is kind of a high-level idea of what we went over last time. We have proven that the constructed inequality is in fact a valid inequality. We have proven that the constructed inequality does cut off the obtained solution. From this point of view, it's a valid algorithm. But I'm not sure. So I would like to stop in a bit more details, explain in slightly more details about on an example how exactly this fractional cutting plane algorithm works. Before we switch to the example, I would like to know if there are any questions, since I have reminded you a little bit of things that we have covered last time. Are there any questions regarding the proof or anything? If it's all clear, let me consider the Gomori's algorithm example. Let's consider the following, actually two-dimensional integer programming problem. We have a linear objective function and 3 constraints, and also additional set of non-negativity constraints for the 2 variables that we have. After the solution of the IP relaxation, we can do the separation of the variables into basic and non-basic, and we can essentially equivalently rewrite the problem of optimization over 2 variables, converted into the problem of optimization over 5 variables. Can anyone tell me what exactly are the basic variables in this case in our new relaxation in the rewritten problem.
The basics x1, x2, x5.
Right. Yeah. It's but basically it has to be three variables like first of all it has to be three variables, and also they shouldn't be included into the objective function, and those are x1, x2, and x5. They should be three variables because there are three equality constraints. So basically here is the optimal solution to the LP relaxation. We can see that only one of them is an integer solution, and therefore it's not actually like three of them are integer valued, but two of them are not, and therefore it's not a feasible solution for us. Therefore, we need to we could have applied branch and bound approach, but in this case we would like to apply the Gomorrah's algorithm just to illustrate how it works. So the first step that we need to do here is to pick which in which row we are like on which row we are from which row we're gonna start our algorithm, from which row we're gonna take our step, and we are picking the first row. And in the first row, the first variable is the basic variable, and x1 is actually a variable that takes a fractional value in the optimal solution of the LP relaxation. We produce a cut. Here is the resulting cut that we are producing according to this formula over here, just using these coefficients essentially. And this cut is an inequality, obviously, because it's it should be an inequality, and we noticed actually last time, even during the last lecture, we have noticed that the slack is has to be an integer value like in this inequality. Therefore, we can rewrite this inequality as a pair of a slack, like an equality constraint, and a constraint on the value of slack being non-negative and integer values and integer value. Therefore, our new linear programming relaxation will now have an additional equality constraint and also an additional constraint on the value of the slack. So we add them both to the constraints. So after we have added the cut, we solve a new LP relaxation. We get a new like a new solution. In this case, so now we have like four basic variables. They are x1, x2, x3, and x4. x5 and s are both non-basic variables. So here is the equivalent reformulation. So it's not the original formulation that we have got after we have added the two previous constraints, but this is the reformulation that we have constructed after we have solved the LP relaxation. And here is the solution to the LP relaxation. Here we again have three integral valued components and two non-integral valued components, in addition to like a value of s that is not mentioned here. Now we can pick the second row because the second row corresponds to the basic variable x2, which is also fractional. So we are picking the variable, the second row and the second variable, and we add a corresponding cut that can be easily written down as 1/2 of x5 is greater than or equal than 1/2. We are again like reformulating this this inequality constraint as an equality constraint and adding a new dummy variable to our LP together with the resulting equality constraint. Like why do we care about what exactly are the constraints that we're adding? Well, like since our problem here is in standard form, it has only equality constraints and non-negative constraints. We would like to keep it like that, just so it's easier to reason about what is basic and what is not basic. It doesn't really matter, but it's normally more useful to do that. So after we have resolved the LP relaxation for the third time now, we end up with an equivalent reformulation of our original problem. Now it has essentially 7 variables. All of the variables corresponding to x are basic, and x1, x2, x3, x4, and x5. The only non-basic variables are s and t, and our xLP is in fact an integral valued vector. Therefore, we have like by solving this LP relaxation, we essentially have recovered the solution to the original IP problem. If we try to imagine on a plane the solution to this problem in terms of the original variables, I just remind you that originally we had only 2 variables, x1, x2. We will see the following picture. So the original constraints are like this. So this is like the solid lines are representing the original constraints, and here are the corresponding the points that correspond to the optimal solutions that our LP relaxations have converged to. So in the very beginning, we have converged to this point 20/7,3. After we have added a cut number 1, this cut that cuts off the original point of the solution, our second round of the relaxation have converged to this point over here, 2,1/2. And after we have added a corresponding cut, our LP relaxation has converged to 2.1, 2,1, which is a point over here. So this is essentially how all of the cutting plane algorithms would work. They would like sequentially cut off parts of the original space, eventually leading to you converging to a point that is feasible for the feasible set of the IP problem. By the way, this is the kind of the front of the optimization kind of. This is kind of the optimization front. So this represents the function, the objective function for x1 minus x2. So kind of you kind of trying to push this front as far as possible to maximize the eventual objective value. Are there any questions regarding the Gomorrah's algorithm and how it works and how exactly mechanically we can implement it? No questions? Okay, sounds great. Now we are going to kind of skip to the next part, which is combining the cutting plane idea with the idea that we have had before, which is the branching bound idea. Basically, like before we, so the next kind of big step for that is the Bender's algorithm, which is quite useful and actually one of the commonly applied in practice algorithms for the solution of mixed integer programming problems. Before that, I would like to illustrate the idea of a branching cut algorithm with an example from Knapsack. Okay, so let's take a look at this example. Let's say that we have a knapsack problem. Basically, we are optimizing over the set of binary variables, like 0, 0, 1 to the n, subject to a single inequality, like linear inequality constraint. Our coefficients are positive. We have seen that it's like we can assume this without loss of generality. I think a couple of lectures before we did spend some time on this. And our like the set of variables from 1 to n is going to be denoted as the capital N. Let us introduce a couple of like additional inequalities that we can use in order to cut off points from our feasible set. So the definition is for a cover, a set C, which is a subset of the set of variables, is a cover if the summation over all of the variables in the set C of AJ is greater than B. We say that a cover is minimal if in case we are dropping any member from that set, the set stops being a cover. So basically it's the minimal like number or minimal amount of items. If we are talking about like a knapsack, then we have items that we are putting into a knapsack, and it's the minimal number of items, or the minimal set of items that we cannot put into the same knapsack. So note that C is a cover if and only if it is associated with the incidence vector xc that is infeasible for the set capital X, meaning that. So what does it mean for a set C to be associated with an incidence vector xc? Well, basically xc is a vector of zeros and ones, where we have a 0 if the corresponding variable or the corresponding index does not belong to C, and we have the value of 1 if the corresponding index does belong to C. Is the notion of cover clear? Are there any questions regarding the notion of cover? Okay. Covers allow us to construct inequalities. Cover allow us to construct inequalities for the knapsack set. The very basic inequality is called the cover inequality, which is saying that if we have a set C which is a cover, if the summation over J's for like which does belong to the cover of AJ's is greater than B, then okay, so this is basically the definition of a cover, and Okay. So basically the inequality, let me switch it over here. Okay. So the proposition that I'm trying to prove here is that if the summation over j's in C, not EC, but just C, of xj is less than or equal than the number of elements in C minus 1, then it's a valid inequality for the corresponding set. So let me okay, I cannot really write that. Oh, I can. Okay. So it's basically like this. So if you have a cover, this the summation over j in C of x j less than or equal than the number of like the number of elements in C minus 1, this this inequality is a valid inequality for a set for the set X, the set capital X, if C is a cover. Sorry, I like this is a proposition that should have been put instead of this definition. So the proof for this is kind of quite intuitive. We show that if we have xr, some incidence vector for a set R, it does not satisfy the inequality, so it doesn't satisfy this inequality specifically. Then xr does not belong to capital X. Obviously, this would be sufficient for us to prove that this is a valid inequality, just because this is all like we just want to make sure that this inequality does not cut off any feasible points. And so basically we like we would need to make sure that if it cuts off a point, because a point doesn't satisfy the inequality, so if it cuts off the point, then the point does not belong to the original set of capital X. So let's assume that that xr in fact does not satisfy the inequality. Just means that the following inequality holds: the summation over j in the cover xjr is greater than the number of elements in C minus 1. Then the number of elements in the intersection of R, of the set R, and the set C is equal to the number of elements in C. How to know this? Well, basically on the left we have the number of elements that belong to R and C at the same time, and on the right we have like a number that is basically this number minus 1, and we know that this thing is greater than this thing, and it cannot be less, therefore it's equal. And thus we conclude that C is in fact a subset of R. In this case, we can just we can just write down that the summation of over all j's of aj xj xjr is equal to the summation over all of r's of aj's, just because our xj is xjr is a binary number, which is greater than or equal than the summation over all c's over all j's in C of aj, just because the C is a subset of R. Therefore, this inequality holds, and which by assumption is greater than B, just by the definition of a cover, and therefore XR cannot belong to the set of capital X. So basically, this proves that the corresponding set is in fact a cover. is in fact about inequality if it's a cover, if C is a cover. Are there any questions regarding this this inequality? Okay. So here are like some examples for this inequality in particular. So, for example, we can take a cover consisting of elements 1, 2, and 3. It would correspond to this inequality if we show that it's a cover for real. To show that it's a cover, we just need to add like sum up 11, 6, and 6 and show that it's essentially greater than 19, which is obviously the case. And also we need to show that basically if we are yeah, essentially this is enough for us to construct an inequality like this. Right. So the next inequality is the following. Are there any questions regarding that?
Sorry, can you go back a slide?
Sure.
So, okay, so from what I understand, it's like you create the first valid inequality by saying, let's look at x1, x2, x3. The coefficients of it in the constraint is 11 plus 6 plus 6. So then that means that if we take this x1, x2, x3, 11 plus 6 plus 6 is 23. So that's greater than b, which is 19 here. So therefore, x1, x2, x3 is a cover, right?
Right. Yep.
Then since it's a cover, we can create a valid inequality by saying that x1 plus x2 plus x3, the cover is less than or equal to the cardinality of the cover set minus 1, which is 3 minus 1. And so that's our cover inequality.
Exactly.
Specific to the knapsack problem. Right.
Yep. Yep. Exactly. Thanks. This is precisely what it is. Similarly, we can prove the following proposition, which is like strengthening in a way for the previous one. If C is a cover for X, then the following extended cover inequality is true, like holds. The summation over J in E of C, where E of C is like an extension of C, with all of the variables for which corresponding coefficient AJ is greater than any of the coefficients AI for all of the elements that are already in C. So, for example, if we are looking at this example, we can take a cover 3, 4, 5, 6. So it's 3, 4, 5, and 6, and then we can add, for example, like the extended cover is gonna include, for example, the coefficient of 1, just because 11 is greater than all of the coefficients in front of the variables that are already in the cover. So 11 is greater than 6, it's greater than 5, it's greater than 5, and greater than 4. Therefore, 1 is gonna belong to the extent cover, E of C. Here we can see that 1 belongs there and 2 also belongs there, because 6 is greater than or equal than everything else. Therefore, our new inequality is x1 plus x2 plus x3 plus x4 plus x5 plus x6 is less than or equal than 3, which is like better inequality than just x3, x4, x5, x6 less than or equal than 3. Right. So it's basically it's called to be dominated by the other inequality. Should Okay, let me actually not spend too much time on this. Let's take a look at the example how we can apply this to the branch and cut. Like how can we use branch and cut idea here? Um, so like how can we combine the ideas of branching and cutting and the same like into the same algorithm on the example of this knapsack problem in this case. So we are considering the 0-1 knapsack problem that has a particular objective function and a single constraint, right? And it's defined over 0-1 to the 7th degree. So our first node in the branch and cut. So the branch and cut, just like branch and bound, it also consists of nodes, but also we add some like iterations to our nodes. The first node is just the problem as it is. So we do not add any additional constraints at this point. Our ZLP, our solution of the linear programming relaxation has a value of 50.615, and the LP solution is has a single non-integral variable. Therefore, it's not feasible for the original problem. Let's take C like a cover consisting of 3, 4, and 6. Let's check that it's a cover. So we have 3, 4, and 6 that in total they give a bigger value than 31, obviously. Therefore, it's a cover indeed, and we can construct a corresponding extended cover inequality that consists of actually 4 variables: x3, x4, x6, and x7, because x7 belongs to the extended cover, because 22 is bigger than everything else, all of the other coefficients. So the inequality is x3 plus x4 plus x6 plus x7 less than or equal than 2, and we add this inequality to our problem. This brings us to the iteration 2. We solve the LP. We write down the solution, still not feasible for the original problem. We add a new cut, and we add this new we add a new cover, and we add the new extended inequality to the constraint to the original problem. It's important to understand that we did not remove the previous inequality, right? So we just add additional inequalities. And on iteration 3, we repeat this again. We again get a solution that is not feasible for the original problem, and we are adding another cover, another extended cover inequality. And now we conclude that we have added 3 cuts. So we really should stop adding more cuts and try to branch instead of adding cuts. So our solution of the LP relaxation at this point is takes the value of 45.5, and the corresponding LP solution is still fractional. So our branching tree at this point looks like this. We are branching at the variable number 4, this one, and it can take 2 values: x4 is equal to 0 or x4 is equal to 1. So we are getting the 2 new nodes for the branching. Considering node number 2, which corresponds to branch x4 is equal to 1, so that now this variable over here will always stay being equal to 1. We are on the first iteration, we are adding a new cover inequality, and on the second iteration, we are obtaining an LP solution that is binary, that does not have any fractional components. So the new lower bound for the problem at this node is equal to 41. We can prune the node by optimality. The node 3 corresponds to the branch x4 is equal to 0, we have to take 3 iterations before we actually converge to a solution of the LP relaxation corresponding to a binary vector. And the new lower bound for the solution is equal to 44. We can again prune the node by optimality. But at this point, we can take a look at the branching tree and notice that our node list is empty. Our optimal solution z being equal to 44, and we have a corresponding value for the solution vector. So basically, the solution has been located in the set corresponding to the node number 3. This approach like turns out to be more desirable just because the number of branches is smaller, and sometimes it's easier to add inequalities like this instead of trying to branch, because like essentially branching every time splits your problem into 2, while if you just add inequality, you kind of leave the number of nodes that you have to process on the same kind of level. So this is the idea of the branch and cut algorithm, the high level idea. Are there any questions regarding this? How we did this?
So to clarify, it's kind of like at each node you have a choice of either continuing iterating on cuts, right? So spending your runtime on cuts, or you can say we have to, whatever reason we have to, or let's branch into another node. And so then it's like the sort of, I guess, the difficulty in trying to balance like branching versus cutting at each node, or
precisely, yeah. So you're right. This is up to the designer of the algorithm. Like one of the applications of like, for example, machine learning is to try to learn, like if you have a stream of problems that are being formulated in a particular kind of space of engineering, and you can try to tune your hyperparameters of the branch and cut algorithm to understand better when exactly you need to stop cutting and start branching, or the other way around. Here we assume that in our cut and branch and cut algorithm we have a limit on the number of iterations, which is equal to 3. So here, when we have hit the iteration number 3, we just stopped cutting and started branching, and I assume that the same thing would have happened over here. So if we were not to find a binary vector over here, we would stop cutting and started to branch. Does that make sense? Yeah, cool. All right. So this is great. Let me come back to the like more general kind of approach to branch and cut. So far we have seen the example of an abstract problem, and we have had specific kind of very clear way of how to construct inequalities for the how to construct valid inequalities for the knapsack problem specifically. Bender's algorithm is much more general in the sense that it can work not only with the knapsack problems, but also with the integer problems and even the mixed integer programming problems. Therefore, since it's so kind of broad in the applications, it's quite successful and very popular, especially for the problems where we have the number of real valued variables much greater than the number of integer valued variables. This is precisely the situation in which Bender's algorithm is performing the best, and it's kind of quite a common thing to observe in the applications of mixed integer programming problems. So let's consider a mixed integer programming problem consisting of a linear objective. Like we have two variables x and y. X belongs to a set of capital X that is a subset of the set of integer valued vectors with non-negative components, and y are the real valued vector belongs to the set of real valued vectors with the non-negative components. So we have a linear objective function subject to a set of inequalities that is basically written down as a general set of inequalities. F is the matrix that corresponds to the variables, the integer valued variables, and G is the matrix that corresponds to the real valued variables. Let us introduce a function, a new function phi, defined over all the possible values of x. Actually, not even necessarily integer values of components of x, but actually but essentially it can be defined for any vector x. So how it's going to be defined? It's going to be the maximum, defined as a maximum over all of the vectors y's of hy, subject to gy being less than or equal than d minus fx. Given this definition, we can conclude that our value of the optimal solution to the original problem we are interested in, z, is equal to the maximum over all x, like small x being in the capital X, the set capital X, of the function cx plus phi of x. How to understand that this is indeed the case? Well, basically, we are not restricting the possible set of the values of the objective function by replacing this hy with the phi of x, just because if hy can take a particular value, then it can then phi of x also can take the same value under the same condition of under the same value of x under which hy takes its value, because because basically if a particular y corresponds, brings a particular value to hy, then the same kind of value of y will be feasible for this problem over here, and it will bring the exact same value of hy to this problem, and therefore phi of x will take at least the same value of hy as it was over here. Is it clear why this maximization problem and this maximization problem are equivalent? Are there any questions? Okay, if there are no questions, I would like to define a set U, a set of essentially dual variables for the problem that is defined with in the definition of phi of x. So here in this problem, this is a very basic linear programming problem where h is the vector of coefficients in the objective function, g is the matrix corresponding to the inequalities, and d minus fx is a vector corresponding to the right hand side. And since x is not a variable in this formulation, basically this entire thing is a constant, and so we have just a simple linear programming problem. Therefore, there must be a dual for that linear programming problem that has the same optimal value as the original, and this set U corresponds to the feasible set of that dual problem. By duality, by this logic, the solution of phi of x is equal to the minimum of U over the set capital U of the value of the vector U times the right hand side in the primal problem, which is d minus fx. So it's U times d minus fx, which is the dual problem for this one. I hope that I like this is there is no doubt here. Now we can try to write down, like, let's try to study this set U more precisely. Let's write down the extreme points of the set U, which are gonna be US. There are capital S of them. And let's write down the extreme rays of the set capital U, which are going to be the VT, and there are capital T of them. So what, like, are there any questions regarding what is extreme point and what is the extreme ray?
What is an extreme ray?
Extreme ray is in the direction in which you can like essentially go to infinity, but it also, like, okay, let me actually give an example of this. So here you have three extreme points, 2 over 5, 1 over 5, 1/2 of 0, and 3 over 2. And you also have two extreme rays. One goes in the direction 1, 3, and the other goes in the direction 3, 2. Basically, it's the directions in which you can still go into infinity while still being like inside of your feasible region. But if you kind of deviate from this direction, you will get outside of the feasible region. Does that make any sense?
So it's okay. So it's the idea of direction. It's like unboundedness, basically, of like,
right. Yeah,
we're unbounded in this extreme ray direction, and then but more precisely, so that, because obviously there'd be like, or more precisely, it's like, I mean, here we can see it's on the inequality, or on the inequality line, but is it basically just like you don't, because I can see that, like, if you deviate upwards, like if your slope increases of the extreme ray, like, then you're not going to be feasible. But then if your slope decreases, right, then you would still be feasible, right?
Yeah. So basically, you can, like, there are multiple like formal definitions that are possible.
Okay, sure.
But the one that you like, that is more like the most intuitive as for me, it's like, if you deviate in any if by deviating in some
Okay. Yeah.
you will get outside of the cone, then it's an extreme ray. So like a ray,
that makes sense.
Yeah, so the ray is a direction in which you can wander into infinity, and an extreme ray is a direction in which you can wander into infinity. But if you deviate in some specific direction, like in some like, if you deviate from that direction by a little bit, then you will like the corresponding rays will not be feasible ray anymore.
So, for example, like if you just drew a line in the middle, that would be a ray, but then it's not an extreme ray because you could deviate to the, like, upwards or downwards a little bit, and then it would still be probably be feasible or not. But then the extreme ray, so, yeah, okay, that makes sense. Thank you.
Okay. All right. So Right. Then we are saying that the corresponding problem, the problem corresponding to 5x is feasible, meaning that the 5x is greater than minus infinity if and only if vt times the right hand side, the d minus fx, is greater than or equal than 0 for all t. So for all of the extreme rays, we must have that if we go in the direction of this extreme race of this extreme ray, we will not be able to improve our objective function. Like, and our objective function is in fact given to us with this d minus fx in the dual problem. In the dual problem, our objective function is given to us with the coefficients of d minus fx. Are there any doubts why this could be true? Is this obvious to anyone? Okay, so yeah, so basically this feasibility requirement is equivalent to the requirement that for all t, for all of the extreme rays, the following inequality holds. Then we write down like we essentially like from the geometry, we know that if there is a solution, an optimal solution to our linear programming problem, then there must be a solution to our linear programming problem that is an extreme point. Therefore, we can say that the solution to our 5x, which is over here, is the minimum over all of the expressions us times d minus fx, just because like we have like this way we just try all of the extreme points that we have in our set. We plug it in, we plug them into the objective functions, the objective function, and then pick the one that corresponds to the minimal objective value. And we know that the minimal one will give us the optimal solution for the linear programming problem. Is like other questions here? Is it clear? Okay, so if there's nothing that anyone is saying, then I think I can spend actually some time explaining this this part.
Wait, sorry, could you explain the extreme? So I think I get the extreme points part, because it's just like linear program theory. We know that like the extreme points are the possible
yeah,
like the solution. So that makes sense. You just check all those solutions.
right.
I'm still a little iffy on like the previous part where it's like the if and only if the extreme ray.
Yeah, that
like,
sounds
yeah.
It makes sense. So so we are doing minimization, right? Let's draw our extreme rays. So like let's say that we have a space. Okay, let me see where should I write it down. Do I have any white space over here? Okay, let me write it over here. So let's say that we have our space, and there is like a polytope, and it has some extreme rays that are going into the infinity. And now I'm saying that let's say that like my optimization problem is trying to optimize in this direction. Like I'm trying, but basically there is a front of my linear objective function, and I'm trying to push this front as far as possible while I'm staying within within the feasible region of the problem. In which case my problem will have an optimal solution. My problem will have an optimal solution if the directions of this race that can go into infinity is not like that does not have any positive slope with this direction over here. Because if it has, then I can just go like I can take one ray out of the set of rays and just go in the direction of this ray into infinity and decrease my function as much as possible, and therefore there will be no like that there will be no limit on the value of the objective function. Therefore, it will be an unconstrained problem, right?
That makes sense. So like the idea basically is just like you don't want the slope of the extreme ray to coincide or like align with the optimizing direction, whatever that's based on the objective function. So because if it is, then you go infinity, right?
Right. The angle between those two must be greater than 90 degrees, and basically the angle is being captured by the inner product between the two vectors, and that should be in our case greater than or equal than 0. Sounds good? Does that explain? Okay, cool. Now back to this a point with the extreme points. So we have this like minimization over a finite set, and we can actually instead of minimization over a finite set, we can use the trick that is very similar to the one that we have used when we were considering max-min problems. We can just instead of using minimization, we can assume that there is a lower bound eta on all of the values us times d minus fx. So let's say that this is going to be s, and this is going to be us times d minus f x, and our values are located like this. Like this is for the first one, this is for the second one, this is for the third one, and this is for the fourth one. And we have eta that is a value that underscores all of them. Like there are obviously many of them that have a smaller value than like all of these numbers, right? For all s from 1 to s to the capital S, and then the value of the minimum among these blue points will coincide with the maximal lower bound, which is the maximal value of eta. Therefore, phi of x is equal to the maximum over eta in all of the real numbers of eta, such that etas are the lower bounds for all of the values us times d minus fx for s from 1 to capital S. Is this obvious to anyone? Is it obvious that these two problems are equivalent? Like phi of x that is defined over here and phi of x that is defined over here.
I don't think it's obvious, but I kind of see the connection.
Um, let's like
Yeah.
we can try to prove it more kind of formally. So like do you see the relationship between this picture over here and this like similarity between these two problems?
Yeah, I think it makes more sense now.
So basically
More like it, yeah.
we are trying to find the maximum over all of the lower bounds on us times d minus fx.
Yeah, that makes sense. So it's like it's kind of similar to what we did before with like the when we had a max min problem, right? Like
Yeah,
where we would encode the inner min or the inner max or whatever it was using inequality, and then just say that like because we're maximizing, so in this case maximizing eta, that's going to push up the lower bound, and then we want to push up the lower bound all the way such that
yeah,
while
precisely.
the lower bound is still, yeah, okay, that makes sense. How about it?
Yeah, this is like we would need, if we were to prove it, like this proof would be exactly the same as we had in the beginning of the semester when we had max and min. Yeah. Okay. So now putting this like all of this together, basically this point over here and this point over here, and also this point over here, putting all of this together, we can sorry. So we can write down that our value of z is equal to the maximum over x's that belong to capital X and over all real eta of cx plus eta, subject to two sets of constraints. One set of constraints correspond to the race, the extreme race, and the other set of constraints correspond to extreme points, right? Basically, it's the it's this constraints to say that phi of x is greater than minus infinity, and it's this constraints like basically this constraints over here that correspond to this constraint over here, right? And we have put it we have put it into the like instead of the definition of the phi of x. So this sets of extreme race and extreme points, S and T, are typically very, very large. They're exponential in the number of, like in the size of the original problem type typically, and therefore it doesn't really make much sense. Even though it's an extremely like nice problem at this point, it's way too big for us to solve it, and therefore we will instead of solving this problem as it is, we will select subsets as dash and t dash of the original sets of inequalities from 1 to capital S and from 1 to capital T, and let px be a formulation for the set capital X. Then the linear programming relaxation of the original problem that we will consider from now on can be written down as follows. Here we have now it's still a maximization, but now it's a maximization for x belonging to the formulation of the set capital X, and eta being a real number of the function cx plus eta. So the objective function is the same. Now the number of constraints is being reduced, and also optionally we can consider a number of upper and lower bounds on the values of each individual variable in the problem, just because we would like to kind of introduce possibility to do branching, and so basically this part will correspond to the like enumeration tree bounds, like the bounds that correspond to our enumeration tree. in the branching boundary. So once we have got this like linear programming relaxation of the original problem. So obviously it is a relaxation, but because it has a fewer number of constraints, and here this thing over like this thing is a relaxation of the set capital X, and also this inequalities, like the number of these inequalities is like have got reduced. Therefore, like we have increased the feasible set for the values of X and the values of eta. Okay, so since it's a relaxation, let us say that XLP and eta LP are the optimal solution of the LP relaxation, and let us assume that CXLP plus eta LP is greater than or equal than some lower bound that we have had from the prior experience on the value of Z. Because if it's less than the lower bound, then we would just prune the corresponding branch, and that's it. We would be done. So we should assume that XLP plus eta LP is greater than or equal than our lower bound. So having this solution, let us solve the minimization problem that basically is the dual of the problem defining phi of X originally. So it's a minimization over the dual variables U over basically the set capital U that we have defined before, but now I just wrote down UG greater than or equal than H. And the objective function just like the one that we have considered just now. Now we can consider 3 different cases. First, the corresponding problem can be unbounded. If it is unbounded, then we have found a new direction of like a new extreme ray, because basically, for example, essentially all of the solvers for the LP problems, for the linear programming problems, will find you proof of unboundedness if a problem is unbounded, and this proof of unboundedness is going to be an extreme ray. Therefore, if it's unbounded, we have found an extreme ray, a new extreme ray, and we can add it back into our formulation over here, and this extreme ray will never appear again, and it will prevent us from getting the same kind of same solution on this stage. Therefore, it kind of cuts off the corresponding case. If our problem of finding phi of X LP is bounded, and it's bounded with phi of XLP, so basically this is the optimal solution to this problem, phi of XLP, which is less than eta LP. In this case, we have found a new extreme point of our capital U, and if we have found an optimal value for the phi of XLP, which is equal to eta of LP, then basically there are 2 options that are possible still. It's that XLP, the corresponding XLP is like does belong to the capital X, then we can prune our corresponding branch by optimality, and if XLP does not belong to the capital X, we can continue we would need to continue branching. I just need to return to the second case and say that if we have found the US extreme point, then we can come back to this formulation, add an extreme point over here, and resolve once again. So we will continue adding new extreme rays and new extreme points until we have found 5xp xlp that is equal to eta lp, and then we either prune the branch by optimality, or we will have to continue to branch. Now, it is important to ask ourselves a question of why we cannot find, for example, a phi of xlp that is greater than eta lp, which like theoretically it could be wise to ask this kind of questions, right? In reality, we just see that our us d minus fx is bounded by eta, by the value of eta, and if we have but basically we should not expect and our u basically is the, like, this is one of the use that we can possibly obtain, and this is one of the use that we will find along the way if we have found something that is less than eta lp, and if we have added basically the largest u that, like, the u that corresponds to the largest value of the objective function is the eta lp, just by the definition of the eta lp of the variable eta. So I would like to show you so this is basically the Bender's procedure. I would like to show you the implementation of it basically through an example. I hope that by demonstrating the example, this this entire algorithm will be more clear. And then if there's any question regarding the algorithm after the example, I will come back to the algorithm and explain it once again. So let's consider the mixed integer programming problem. This problem consists of an objective function, a linear objective function, and two inequalities, general form inequalities. A single inequality on the value of x. X's are being integral valued non-negative variables, and y's being just real valued non-negative variables. So basically, these two constraints define the set capital X, and y's are being just real variables. So basically, in this case, our matrix F consists of four numbers, 2, 4, 3, and 5, and our matrix G consists of six coefficients, 4, -2, +3, 2, 3, and -1. And our vector D consists of two numbers, 12 and 10. The corresponding dual polyhedron, as we have defined it, will take the following form: U being equal to the set of, so first of all, we have two dual variables. So the corresponding, U is gonna be a subset of a two-dimensional space. In this case, we will denote them as U1 and U2, the corresponding variables. And now we have so there must be five. Since we have five variables, there must be five constraints in the dual, defining the dual space. But here we have only three. The first constraint, for U1 plus 2 U2 greater than or equal than 2, this corresponds to this to the variable Y1. So it's 2 plus 4 less than or equal than 2. 4 plus 2 less than greater than or equal than 2. and the second constraint corresponds to the variable y2, and the third constraint corresponds to the variable y3. Basically, this is oh yeah. So I just have to say that it's enough for us to so like we will only have three inequalities just because our G is a matrix that is 2 by 3. We have only three real valued variables here. Therefore, we will only have three constraints. And the corresponding corresponding set U has three extreme points and two extreme rays, 3, 2, and 1, 3. Let's take a look at this. So this is our set U. It has three extreme points over here, and also two extreme rays, which are basically like 1, 3, and also 3, 2, like this. And therefore, our set is this shadowed region, the capital U. Also, the same set can be rewritten in the following form, where we have the convex combination of our extreme points and plus a conic combination of the extreme rays. So any point that belong to the capital U can be written as a convex combination of the extreme points plus a conic combination of the extreme rays. This is just a fact from convex geometry or from polytopes. Rewriting the Bender's master problem, we will have 5 inequalities in total. 2 of them will correspond to the extreme rays, V1 and V2, and 3 of them will correspond to the extreme points, U1, U2, and U3. Right. And we also need to write down the inequalities that correspond to the set capital X, and we have only 2 variables that correspond to x1, x2 that are integral, and also only 1 real valued variable eta. So since we have this, at this point, it's very clear why exactly we have assumed in the very beginning that the number of variables, the number of real valued variables is way less than the number of integral valued variables, just because now instead of all of the real valued variables, we have only 1 real valued variable, which is a great a great simplification of our problem. Now, this Bender's master problem will never be solved as it is, just because it's way too many inequalities. So we will start by producing an initial node number 1. Start at the initial node with only 1 bound for the constraints on X, and the valid upper bound on the optimal value of 5x, just so that we, do not actually get infinite values. So we constrain eta to be less than or equal than 200, just so we know when exactly we have hit infinity. The solution, the optimal solution for this problem is z equal to 222, and x star being equal to 2, and eta being equal to 200. So basically, we have hit the infinity. the corresponding value of 5x is like can be calculated from the d minus f of x star, which is 12, 10 minus the matrix f times the vector x1, x2. And so our right hand side, our new right hand side, is equal to 0 minus 6, just because 12 minus 12 is 0 and 10 minus 16 is minus 6. And if you take a look at it, how it's located on this graph over here, it's like 0 minus 6 is a vector that looks this way, right? And since we are doing minimization, since we are doing minimization, we are interested in going in this direction. Okay, how do I change the color? Here we go. I'm interested in going in this direction in order to improve my the value of my objective function. And going in this direction is quite possible, just because I can go along this edge over here all the way into infinity and never get tired. So just essentially any linear programming solver would tell you that the corresponding optimization problem, the optimization problem corresponding to the solution of 5x is unbounded, and the corresponding extreme ray is V2, which is the ray 1, 3, which is written over here, and we have bounded. Therefore, now our new set t dash is going to be equal to 2. So it's going to consist of a single member, and the corresponding constraint is 11x1 plus 19x2 less than or equal than 42. And we add this constraint to our master problem. Are there any questions regarding how we solved the problem for 5x? Okay. So now, since we have added this new constraint, we can we can transit to the second iteration and solve the LP relaxation for that. So after the solution of the LP relaxation, our new optimal vector x star is equal to 4 over 11,2, and our eta is still equal to 200. So the solution of our 5x star, after we so basically we repeat the same thing once again. We take D, we take F, and we take the new x star, and we calculate the new right hand side for in order to solve the problem corresponding to 5x. We have solved the problem corresponding to 5x. We have found the value of 12 over 11, which is much less than 200, which is the value of eta star. The extreme point corresponding to this value, 12 over 11, is equal to u1, which is 2 over 5. Sorry, which has the components 2 over 5, 1 over 5. If we take a look at this example over here, we would see that it's this point over here, which we have found. And now we can add this extreme point to our set as dash, and the corresponding and we can add the corresponding constraint to our master problem. Now we have a new master problem on iteration 3. We have a new master problem with two new inequalities. the corresponding solution is 2, 1, like 1.0526, and the corresponding eta is slightly over 1.25. The solution of the corresponding problem of the problem corresponding to 5x star gives us the same value of eta, like the same eta star, and the solution, like since the solution of x star is not integer, we would need to branch our algorithm at this point, and create the node 2 by branching on the variable x2, because our variable x2 is not integral. So x2 is either less than or equal than 1, and the node 3 will correspond to x2 being greater than or equal than 2. So this is our branching tree at this point. On the next iteration, we resolve the problem, get in fact an integer solution for x, and we again get like after the solution of the problem for the 5x star, we'll get the same value for the eta star, and since our solution x star is integer, we can assume that we have solved the problem corresponding to this particular branch, and the corresponding value is 16.4. The corresponding solution of x star being equal to 2, 1, and y star being equal to 0.10 and 1.2 is like it needs to be stored, and the node can be pruned by optimality. Now, returning to the node 3, the first iteration gives us, so like in the node 3 we still have the same inequalities that we have added on the iteration 3 of node 1, but now we have added a new inequality x2 being greater than or equal than 2, and the corresponding x star, the optimal solution, is like consists of one fractional and one integral value. The eta star is like takes the value 12 over 11, which is exactly the same value as the corresponding 5x star, the solution of the corresponding 5x star. The solution is not integer, therefore we would need to branch at this point, and since our x1 is fractional, we will branch on x1, x1 being less or equal than 0, or x1 being equal to 1. This is the branching tree that we have at this point. So now the nodes 1, 2, and 3 have been processed. Now we have nodes 4 and 5 to process at this point. In the node 4, we have the same two inequalities from node 1, and we also have two new inequalities, x2 greater than or equal than 2, and x1 being less than or equal than 0. The corresponding optimal solution for the LP relaxation is 15.6, which is smaller than 16.4. Therefore, we can prune this node by bound altogether. And in the iteration 5, we have like we essentially, like, this is the problem that we end up with, and after the solution for the 5x, we realize that our like it's the corresponding direction, like the corresponding 5x is infeasible, and basically we are able to find the extreme ray v1 and add the corresponding inequality to our LP relaxation, and the new the new optimization problem, the new LPO optimization problem turns out to be infeasible. Therefore, we complete with the processing of the node 5, which is also can be pruned by infeasibility at this point, and all nodes have been pruned, and the searches can be completed, and the optimal solution have been found in the node 2. Its solution, its value is 16.4, and the solution is 1.2 and 1,2, and the y is 0.10 and 1.2. Which basically essentially completes the entire algorithm. So going from this example, I would like to come back to the original algorithm and say where exactly we have used which case. So we have definitely found and we twice we have found unbounded, like this problem being unbounded, and we have found a new extreme race twice. We have found a new extreme point once, and we have found phi of x being equal to eta at least 3 times, right? And once we have pruned by optimality, and twice we have branched at this point, and we have used this this inequality once in the node 4 in order to prune it out. Are there any questions regarding the example or the algorithm that we have considered so far? I would like to know if it's absolutely obvious why, for example, if phi of xLP is less than eta LP, then we have found a new extreme point. And why do we have to branch if we have found out that phi of xLP is equal to eta LP? Why cannot we do something else? Why we didn't found a new extreme point in that case?
Sorry, could you explain the extreme point, like why it's a new extreme point? Because that's actually not that, or I don't know, it's something in my head.
Yeah, so basically, let us consider the following picture. Let's say that we have 3 inequalities. One is going to be the blue inequality, then we're gonna have a red inequality. So we are in the U space right now. We are considering inequalities that define the set U, right? And let's say that, okay, so let's continue this until the intersection between the two. Okay, like that. So we know that basically we know that our phi takes the minimal value over over all of the over all of the US times d minus f of fx. So this is something that we don't really need to have any relaxations or anything. It doesn't really matter how exactly you you solve it, you will end up with this expression, just because basically you can look at it from this viewpoint. Over, like, you can just say that you are solving this problem up above, and it doesn't really matter like what exactly your sets are. Your set S dash or T dash do not contribute to this to the solution of this problem up above. So this f phi of XLP is the correct number always. Doesn't matter how many extreme points you have found at this particular round at this particular iteration of the algorithm. Now, eta LP is something that is not precise. Eta LP is something that is only guaranteed to be less than or equal than US times D minus fx, only for those only for those extreme points that you have considered so far. Therefore, there might be there might be US that have a value still smaller than your value eta LP, that are not included into this set. Do you agree with me?
Like basically the eta is like not the eta is just it's the same, it's like similar to the phi, but the phi has all the possible extreme points, and then the eta has a subset of them. So then if our values for the eta does not match, that means that we're missing one of the extreme points, and that extreme point is that extreme point is the one that actually, or theoretically, it could be one of the things that leads us to a closer to such that they match, right?
Yeah, that's exactly. Yeah, okay. Yeah. And when, like, if they have matched, then we can conclude that basically, like, basically our eta and our U of S are are the same. Like they have the same value, and therefore by doing this iterations over and over again, we will never we'll cycle ourselves in. Therefore, but essentially there's no way for us to construct new Bender's cutting planes from whenever we have 5x XLP being equal to eta LP, just because our but basically when we have 5 XLP not being equal to eta LP, just means that we have converged to a point over here that is being cut by some cutting plane in our problem, but this cutting plane is not something that we have considered so far. And once we have added this cutting plane, we will converge to one of these points most probably, and from this point on, we don't really have any new cutting planes in our set of cutting planes in our set of valid inequalities that would be able to cut any of these of these 2 points. Therefore, we would have to branch or prune by optimality, but most probably we'll have to branch. I hope that this explains a little bit.
Sorry, just to recap, the third thing of why we have to branch whenever we get to okay, actually, to come back. So initially, let's say we have phi is less than the eta. So then we say that we found a new extreme point, and we keep on doing that until eta equals the phi. And right. So when eta equals phi, essentially, and we'll have a subset. So the phi will have a subset S prime or whatever. And that subset S prime is like a more efficient version of the original of all the extreme points, right? Like it won't have all the extreme points. It'll just have sum of the extreme points. But that those extreme points still achieves the same value as the phi, as having all of the extreme points, right?
Exactly, precisely.
Okay, and then because, so we have it's like we got a more efficiently, like a smaller bag of the extreme points. And then once we're there, you're saying that the cut that we have is such that we can't cut further and get and get more, we can't cut further, so then we have to branch. Because the whole idea is cutting versus branching. Okay.
Yeah, exactly. So this is dictated by the fact that our set, so like this set, the set of extreme points and extreme rays, they describe this constraint exactly. So this constraint is being described exactly, and we will be able to kind of construct enough like by the time we have got here, we are describing our set of inequalities fx plus gy less than or equal than d precisely, but this set X, this set capital X, still can be described with some imprecise formulations. So of this formulation px, there are no assumptions on it, and it can just happen that the description of the set capital X is imprecise, and therefore there is like infeasibility that is not, like, it's not possible to cut it off just by adding more valid inequalities that are actually only related to this constraint and not related to this constraint. I hope that helps a little bit. And also I wanted to say that when you are iterating between these two cases, you're essentially picking a side. So like let's say that our set U looks like this, for example, and it has very like a lot of different inequalities for real, like there are a lot of them, and you are picking a direction, you are picking a side. For example, the direction is this one, and then you are discovering for yourself a sequence of valid inequalities. First you probably discover this one. Okay, change the color. First you probably will discover this one, and then you will discover this one, and then you will discover this one, and then you will discover this one. And even though it's not all of the inequalities that you would need to discover, it's still enough for you to completely describe the set in this direction, like with respect to the like a particular direction in which you are trying to move because of your objective function. This is basically the thing that is being exploited in this Bender's procedure, and actually many other procedures too. So it's really kind of just like trying to explore the geometry of the feasible region, but not like everywhere. You are trying to explore the geometry of the feasible region in a particular direction, and this is like the intuition, the geometric intuition behind the Bender's procedure.
That makes sense. Just it's very complicated, but I think the intuitive, like that makes a lot of sense. You want to save on runtime, you want to save like computational time, so you're not going to explore everything, and you only need to care about that. That makes sense. Thank you.
Yeah. Yeah. So I really just wanted to make a couple of comments about where exactly, like, first of all, where to go from here, because I think I'm about to finish the main content of the lectures, and probably next time we will go over the same kind of things once again, and I will just quickly remind you what we have gone over, and probably there will be some questions before the finals. For the branching cut, I just want to mention that it's basically branching out is basically the same as putting together the ideas from branching bound and the cutting plane algorithms. All of the like mixed integer programming systems use some form of this ideas of the branch and cut. So all of them are doing some like Cplex, Groby, like all of them are doing some pre-processing in the beginning, which is also kind of in a way it's form of adding kind of cutting planes, but it's not a they do not do like cutting planes like in the specific directions. Basically they are just simplifying, like doing some simplification with the like independently on in which direction you're going to be optimizing. So that therefore it's set off as and called a pre-processing stage. And then after the pre-processing stage, most commonly they are just using some version of this branch and bound approach that is most applicable in that specific case. We have seen already two versions of it. So, for example, for knapsack problems, there are this like covering inequalities and extended covering inequalities. Actually, in the chapter, I believe in the chapter 11, there are more, or probably in the chapter 10, there are more like even better cuts that are possible to construct out of the extended covering inequalities that you can learn about. So all of them are being used in the commercial solvers, and they are being improved basically every year. So new branch and cut methods are being deployed. So after pruning and before branching, so like yeah, basically like branching and cutting can be put in different order, and there are many hyperparameters that can impact the depth of the tree and the number of iterations of cutting that you can set up. And there are much bigger variety of different classes of cuts that you can use in your in your algorithms. We have seen the Gomori cuts, which were for the integer programming problems. There are also mixed integer rounding cuts and split cuts that are described, I believe, in the chapter 8. There are the Danzig-Wolf cuts that we did not consider, and like yeah. But by the way, the mixed integer rounding and the split cuts are both for mixed integer programming problems. So Gomori cuts were for just integer programming problems, and the others are for mixed integer programming problems. We have discussed the Bandura cuts, and also there are problem specific cutting planes, such as the one that we discussed for the knapsack problem, right? And there are more of those in the section 14. I would like to also mention the big topic of machine learning and its relationship with the topic of integer programming problems and how they are related to each other. So there are two different ways from which you can see their interaction. First of all, it's the machine learning for IP, for integer programming problems. Basically, it's the direction in which people are going, for example, to try to learn how learn the structure of the integer programming problems that are appearing in a particular in a particular application. Like you can theoretically set up the learning algorithm to try to set up the hyperparameters or tune the hyperparameters of a branch and cut algorithm, or whatever integer programming algorithm you would like to use. For example, like set up the select the branching variables, or decide whenever like whether a heuristic is usable or not, or whatever the billions of decisions that are being made in the integer programming software, all of them can be used, can be made by artificial intelligence that is being tuned to be adapted to a particular application, and that can reduce the complexity of the solution of mixed integer programming problems by a lot. Which is like I would say this is a very like promising topic on my experience. And also the machine learning, which is being, I would say that it's being less studied, which like for example, we have like one of the homework questions was about how to formulate the problem of learning at like two-layer neural net as an integer programming problem. So that like problems like that have been studied for a while now, and there are like interesting directions of research in this area. So this is basically how to like this direction of research is asking the question how to use IP methods in order to learn models for some other applications. So it's kind of a different angle from which you can enter both the topics of IP and machine learning. Probably one very interesting direction of research that I would like to mention here is the direction of neural architecture search. Most commonly, it's being solved by like it's really a problem of discrete optimization problem most commonly, and therefore it can be formulated as an integer programming problem, as a mixed integer programming problem, and there are attempts to put the neural architecture search as a problem that can be solved with Cplex or Gurobi, but it's still kind of experimental, and if you're interested, there are articles on this topic as well. Okay, so I would like to stop here. Thank you very much for your attention. So there will be a discussion section tomorrow, and next time we will go over like all of the topics that we have discussed up until now. I will probably try to find some more examples for you, and yeah, after that we will have exam and conclude for the semester. If you have any questions, please let me know. We can set up office hours and discuss it. Thanks a lot for your attention.
Thank you, Professor.
Bye.
Yeah.
Thank you.